Good morning. Okay. So today we will start chapter 7. Before this, let's start with a quick reminder of what we have discussed in chapter 2. So chapter 2 we have 4 points. So we started with explaining what is meant by pure substances. Okay. And what are the phases of pure substances we have? What is the name of phase change processes from one phase to another one? Then we start to explain what are the resources that we can find several physical properties, value of physical properties for different substances and especially steam. So we have diagrams, we have two-dimensional diagrams, three-dimensional diagrams, and the most important we have steam tables. These are 4 tables. A1, this one, and A2, these two are for saturated liquid and saturated vapor. One, if you have pressure is known or given, the other one if temperature is given. A3 for superheated steam, A4 for subcooled liquid. Then we start to explain, okay, so what if we have different substance and we still need to calculate internal energy? Or if we have open system, we need to find the enthalpy. So in this case, we start with defining what is meant by the enthalpy. And we said both internal energy and enthalpy can be calculated from heat capacity. Heat capacity, we have 2 heat capacity values. Heat capacity at constant volume, CV, this is the one that we are using to calculate internal energy. Heat capacity at constant pressure, CP, this is the one we are using to calculate the enthalpy. And if you have liquid, if you have solid, the value of CV equal the value of CP. Or any changes in the internal energy will be the same value as enthalpy changes. But for ideal gases, CV is not equal to CP. CP is CV plus R, so we have all you need to calculate internal energy and enthalpy separately. Then we start with explaining ideal gas, or in general the equation of a state. We have ideal gas equation of a state, PV equal nRT. Said this one can be used for gases that behave as an ideal gas. What is meant by ideal gas? The volume of the molecules can be neglected. The intermolecular forces between the molecules also can be neglected. This equation is valid at very low pressure values or at extremely high pressure values. Then we have, in order to overcome this limitation, we introduced the van der Waals equation of a state. So this one introduced 2 parameters, A and B. One account for the volume of the molecules, the other one account for the intermolecular forces between the molecules. But still, this one have some limitations. So we said we still need more accurate equation that we can use, because van der Waals itself, it fails because it assumes that the value of A and the value of B are constant, are not changing with temperature and pressure, and this is one of the limitations of van der Waals equation of a state. So chapter 7 we will talk about the equation of a state. Okay, so we'll start with introducing what is meant by equation of a state and what are the uses of these equations of a state. The most important one is the cubic equation of a state, so we'll explain what is meant by the cubic equation of a state, why they are called equation of a state, and why they are called the cubic. And then we have another principle, it's called the principle of corresponding states, also another way that we can use to find the properties of the substances we have. So generally in chapter 7 we supposed to have 4 points to cover. We're supposed to have equation of a state and the principle of corresponding states. Also we have other points that we are supposed to cover, the generalized correlations, aggregated data, group additivity or Jopak method. But these 2 we may not cover this semester because we spend more time on chapter 2. Okay, so just I want to make sure that we finish this part and we have practiced some problems on this one before the exam, which is next Monday, right? Not next Monday, Monday after next week, after the next week. Okay, so based on what we will process next week, so we can go over these 2 points, or we can say this is enough, we can have only the first 2 points, practice them. This only will only part of chapter 7 that we have in the exam. So this is something we will discuss next week together. Okay. Okay. So for chapter 7, as we said, we have ideal gas equation of a state. This one is accurate at low pressures or extremely high pressures. This one is also accurate at very high temperatures. We have van der Waals. This one was a breakthrough. This one, now it's replaced by advanced equations. So what are the equations that we need to study? We have 3 advanced equations that we can use. We have Redlich-Wang equation of a state, and then we have another equation, it's called modified Redlich-Wang. We have Soave, he modified this equation. So it's called the Soave equation of a state. Just when you say Soave equation of a state, we can know that we mean this equation. Or we can call it Soave-Ridley-Schwank, because basically Soave took Ridley-Schwank equation and just he modified it. And we have Peng-Robinson equation of a state. So these are the equations we have. So basically the advanced cubic equations, we have Soave equation, we have Peng-Robinson equation of a state. These are, even nowadays we are using any of these two substances. Okay. So what is meant by these equations? So basically equation of a state, this is an equation that relates the temperature, pressure, and molar volume. And molar volume is volume divided by number of moles. So any equation that relates these properties, these three properties, can be considered an equation of a state. Okay. So what is the other condition? The other condition that all the properties in this equation, they should be state functions. Remember in chapter 1, we said we have properties can be classified as state function or path-dependent function. State function, these are the properties depend on the initial and final condition, regardless of the path, how you reach the final point from the initial point. So this path, it doesn't care about this one, it doesn't affect its value. So if you have relation, this relation or an equation, this equation relates temperature, pressure, molar volume, all the properties you have in this equation are state functions to each other. So this is considered an equation of a state. Okay. So what are the uses of equations of state we have? Equation of a state, so that's one you can use to predict PVT properties of gases. So if you have two properties, you can use it to find the other one. So it relates these three properties together. We can use this equation of a state to find the parameters that we are need to size any pipe or any equipment. And here size mean we need to define the size, and this is part of the design process. Because if you need to design something, you need to know the size of this one. And if you need to size any equipment, then you should use an equation of a state. Okay, so equation of a state, one of the fundamental equations we are using for sizing calculations or design calculations. Also, equations of states are very important for safety analysis. If you need to analyze any equipment in terms of the safety, and if you need to decide any control strategy to make sure that this process is operating at safe conditions, equations of states must be there. Okay, so equations of states, there are a lot of uses for these equations of states we can have. So now we know that what are the equations or why they are called the equations of a state. So the question is why these equations are called the cubic. If we start and remember from chapter 2 PV relationship, so we have this is PV diagram again because the y-axis is pressure, x-axis is volume. So here in this one we have three regions. If you remember this region, region I. Anyone remember what is the phase exists in this region? Do we have liquid or mixture or vapor? Anyone remember this one? Liquid. So exactly. So this region here we have compressed liquid. The second region, region 2, we have a mixture of liquid and vapor. And region 3 we have vapor. So these are the main three regions we have. And each of these dotted lines we have here. So this one represent constant temperature line. So temperature on any of these dotted lines are constant. So if we are assuming temperature is T1, so at this point, the temperature at this point is T1. Temperature at this point is T1. Temperature at this point T1. Here, temperature T1. Here, temperature T1. So each of these dotted lines represent a constant temperature we have. Okay. So these dotted lines represent PV relation at constant temperature. So we can have this area or this line represent the liquid, and then we have this line represent the vapor, and then we have this line represents mixture of liquid and vapor. So if you need for any pure substance you have, you need to put the behavior of the phases with PV with pressure and volume at constant temperature. So we have almost a vertical line, this represents the liquid, then you have horizontal line represent the mixture, and then we have another inclined line represent the phases we have. So if we like take this line, one of these lines to put, so we have, let's put the same colors. So again, this line that represent the liquid, and then we have a line here, this horizontal line represent the phase change, and then we have this line then we have this line that represents the vapor. If I tell you I need an equation that describes this behavior, so the easiest thing we have is to find an equation that fits in all of these lines. So I need an equation. Here we have this one, and then equation that moves horizontally, and then equation moves on this way. So if you can have an equation, if you plot this equation, you have this shape, this straight shape here we have. So this will be considered your equation of the state. The thing is, there is no mathematical equation. It can go almost vertical, then horizontal, then we have inclined. There is no equation can do this. So what we are doing the problem in this area. We can have equations that can go this way. We can have equations that can go here, and then go down, then go up, and then go down again to match this one. So we can have an equation. If you plot this equation, you have this shape. So you have the region that represents the liquid exactly lies on this equation or in this plot. You have the region that represents the vapor lies on this one. Only what you are missing is this mixture region. Because again, we cannot have an equation have this like horizontal line. So this equation we have here, or when we try to plot the behavior of any substance we have, so we have this purple line, this is how this equation looks like, and this plot, it represents what is called a cubic equation. So any cubic mathematical equation, if you need to plot it, you will have it have this shape. So it goes down, goes up, and then goes like this one. Okay, so we have part of this line represent the liquid, part of this line represent the vapor. So at least we have the liquid region, we have the vapor region exactly lies on the equation we have. But the horizontal line that represents the mixture, it doesn't fit with it. Okay, so this is the equation of a state, and this is how we have this dotted line represent our function. So we have, this is our dotted line here, start from here, goes down, and then it continue its path till the end. So far as clear? So this is how they think of having this cubic equation. So again, for pure substance, we have certain behavior. There is no math equation can like capture the liquid phase, the mixture, and the vapor phase. But we can have a plot. It's called cubic equation, cubic mathematical equation. It can capture the liquid phase, can capture the vapor phase, and this is how it looks like. The area of the mixture we have, this one, it doesn't lie on this equation. So we are missing just capturing this region. So far is clear? Okay. This cubic equation, we can divide it into like 5 parts. From this point, from that point, CD, this is line number 1 or part number 1. Then we have CE, from C to E, this is part number 2. Then we have from E to F, this is part number 3. Then we have from F to B, this will be part number 4, and from B to the end, so this is part number 5. So this equation, we can divide it into 5 regions. The first region, this one, CD, this one represents the liquid phase. The region number 5, this one represents the vapor phase. Okay. And these are considered stable phases because in reality they exist. We can have liquid at this condition, we can have vapor at this condition, so these are called stable phases. Okay. Then CE, EF, FB, so these 3 regions does not exist in reality. So they are called metastable phase because in real, if you have any substance at this condition, you will not have like a certain phase, just you will have mixture of two phases together. So these are called metastable phase. Okay, so how we can like name this? So here we have something called stability criteria. We know that we have PV equal nRT. If you rewrite this equation, so we have P is nRT over V. So we have inverse relationship between pressure and volume. So this means if you need to see how the volume will change with pressure changes, this will be negative. This should be less than 0. So any line that doesn't or fulfill this condition, this represents a stable phase. So we have the first line, the DC line. This represents real liquid data. It fulfills this stability criterion. So this is called, or this line represents a stable phase. We have the other line, BA. This one represents real vapor data. So it's called, it represents a stable phase of the substance. It fulfills this condition we have here. We have this line, EF. If you see this line, EF. This line here, if you see how the volume will change with respect to pressure, this one will be more than 0. This line tells you that we have a direct relationship between pressure and volume. This is something against stability criterion. So there is no phase can exist at this condition. So this line represents unstable phase, a phase that does not exist. The line FB and CE, it fulfills the stability criterion. The relationship between pressure and volume are inverse, it's negative, but there are no real phases exist at this condition. So this is why these two lines are called representing metastable phase. They represent a stable phase because it fulfills the stability criterion. But in fact, in reality, there is no liquid phase, there is no vapor phase will exist at this condition. So this is why it's called metastable. It's not a stable phase, it's metastable phase. Just we have the stability criterion. It's fulfilled at this condition, but there is no real phase will exist here. So again, the cubic equation of a state we have here, we have like two lines or two regions represent stable phases, two regions represent metastable phase, and we have one region, the EF line, represent unstable phase. So far is clear? Okay. So why we are discussing all of these things? We are discussing all of these things because when you try to solve the cubic equation of a state, this is how the general form of the cubic equation of a state. We have one property to the power 3. This is why it's called the cubic. One property, the highest power of this property is 3. And because of this, it's called the cubic. If you try to solve this property, for example, or try to solve this equation in order to calculate the molar volume, what is the values or the possible values you can have for the molar volume? 3. So cubic equation of a state, it can give you 3 different values for the properties that it has power 3. So we have here molar volume to the power 3. Just try to solve this equation. You can have 3 different values for the molar volume. Okay, and how this can happen? So let's start with this one. If we try to solve this cubic equation of a state at pressure P1. Okay, so what you will have, if you just find the solution you have here, so try to go at this pressure to cut the plot of the cubic equation of a state, then you will have a single value. Why you have single value? Because this part represents a stable phase. So the stable lines or the stable part of the cubic equation, solving them will give you just one value. Okay. If you are trying to solve it at any other pressure like P2 or 3 or P3 for example, so at P2 you can intersect here, you will have one possible value for U1. Then you have here another possible value for the molar volume. And then if you continue, you will have another molar value that you can have here. So this is why solving this equation of a state can give you, sometimes it can give you one value, sometimes it's possible to have 3 different values for the molar volume. Not for pressure, not for the temperature, only for the molar volume. Because the molar volume, this is the only property we have that has power 3. So the possible solutions we can have 3 different real numbers. We can have same answer, just repeat it 3 times. we can have one real number and two complex numbers. So you can see all of these options. Okay. Now let's assume if I solve it and I have, this is the most common that you can see, I have three like different numbers, similar to what we did here at P2 or P3. So you can solve it, you can have this an answer, this an answer, this an answer. So which value I should consider? Now, do you remember when we said we have a stable phase, we have metastable, we have unstable, right? Now, if you check this one here lies on the unstable line, right? So we usually neglect this one, because this one represents unstable. So the value in the middle value of the molar volume, just neglect it. Why neglect it? Because this one lies on the unstable line. It doesn't fulfill the stability criterion, just we described. So this number you can't use. Okay. So then we have two other values that we can use. We have this possible value. We can have this possible value. Which one of them I should use? Based on the problem you have. If your problem, you have liquid phase, then take the smallest one. So the smallest molar volume, this is the one that represents the liquid phase. If your problem you have vapor phase, then you should take the largest one. So again, based on the points we have, so this point, this is the smallest value that you can get at P2 or at P3. So in the problem, you know that you are dealing with liquid phase, or I ask you calculate the volume of the liquid phase for this substance. So you should consider only the smallest value. If you have the same problem and I ask you find the molar volume of the vapor phase, or in the problem statement I mentioned that you have this substance exist in the vapor, so the vapor or the value that you will use is the largest one. So again, when you solve this equation, the cubic equation of a state, and if you have three values for the molar volume, the smallest one, this is the one for the liquid, the one in the middle, usually we neglect it because this one for unstable, the largest one, this is the one we are using for vapor. Okay, and also you can see here, so here at this intersection, at this pressure value, so this represents the liquid, here at this one, this represents the vapor. Okay. So far it's clear? Any questions? Okay, so this is a general view of the cubic equation. The first cubic equation we have is van der Waal. Van der Waal is considered the cubic equation of a state. This is the first cubic equation of a state we have known. But again, there are some limitations on this equation. So we have Redlich one. They improved this equation by modifying it, and we have this form of Redlich one equation of a state. Then Soave modified this equation, and we have this Soave equation of a state. This one is important, and we are using it. And then we have Peng and Robinson. Peng-Robinson, they developed another form of the equation of state. So all of these are equations of states we have. And this is how, even historically, how they were developed. So van der Waal, we have limitations. Then Redlich and Wang, they have an equation. Soave modified them, and at the end we have Peng-Robinson. So far, we are using the Soave equation of a state. We are using Peng-Robinson equation of a state. These are the most common equations we have. And if you can see, we have in all these equations, we still have pressure in all of them. We have the ideal gas constant. We have the temperature. We have the molar volume. We have the parameter B that represent the interaction between the molecules. We have the parameter A that represent the interaction between the molecules. But here we have some new parameters like alpha, and alpha we have here. And these are the modifications that we are adding in order to overcome the shortcoming or the limitations we have at van der Waal. So just we have a new parameter defined here, it's alpha, and also we have different way of calculating A and B. We are not using van der Waal definition or van der Waal equation to calculate A and B. We have new equations to calculate B, new equation to calculate A, and another equation to calculate this correction factor parameter alpha. As far as clear, this is your question? Yeah. So now, let's get back to see the equations we have. So again, we have Soave, we have the Redlich-Wang equation of Peng-Robinson equation of the state. Similar to what we did for van der Waal, we have two forms that we can represent Soave equation of the state. One of them as P equal RT over V minus P on this one, and then we have in terms of the compressibility factor Z, we can put it this way. Okay. Similar Peng-Robinson equation of a state, we can represent in this one, and we can represent it in this form in terms of compressibility factor. Okay, So we have for Soave equation, for Peng-Robinson equation, we have two ways to present each one of them. The question, how we can calculate A, how we can calculate B. Here in this equation, you cannot see alpha. So alpha can represent it in the equation, similar to what we have here. Yes. So alpha, this one can be represented, or it can be lumped in A calculation, just to simplify the equation we have. So here, we're supposed to have alpha, but we neglect it because it's lumped here in this one. So some textbooks put this, some textbooks, they lump it together. Just when you see difference, so this doesn't mean alpha is cancelled. Alpha is not cancelled. Okay, just the way of calculating A is just modified. We have alpha multiplied by it automatically in the calculation. Okay. So the question here, how we can calculate A, how we can calculate B. Actually, for Soave, we have some equations to calculate A and B, different from the way that Peng-Robinson is using to calculate A and B. But in all of them, in order to calculate A and B, we need three information. You need to know the value of the critical temperature for this substance. You need to know the value of the critical pressure of this substance. And you need to know the value of the eccentric factor for this substance. In van der Waals, you have only critical temperature, critical pressure. Here we have one more parameter increase, which is the eccentric factor. Eccentric factor, this is a parameter that just describes the shape or the structure of the molecule. If we have noble gases, very structured, then the eccentric factor will be 0. If we have spherical molecule that is symmetric, then the value will be close to 0. If the value of the eccentric factor becomes far away from 0, so this means we have a symmetric compound. So this eccentric factor, it represents how the structure is symmetric. If it's more symmetric, so it goes towards 0. Noble gases, which is 100% symmetric, so we have eccentric is exactly 0. So this is a noble gas. Just if you see the structure, it's complete symmetric. So this one, the eccentric is 0. This one here, we have the eccentric can be 0.011. It's not 0, it's not noble, but still we can assume it's spherical. We still have some symmetry in this one. And this one here, we have the eccentric factor, this one that will have value away from 0, because we have asymmetry here. Okay? Then, how we can calculate A and B for Soave equation. So if you have, or if you are using the Soave equation, B is 0.08 times ideal gas constant times critical temperature over critical pressure. How you can find the critical temperature and critical pressure? So again, we have appendix C. This is the appendix that you need to use to find the critical temperature and critical pressure. How you can calculate A? So A, this is alpha, so here we can see alpha right now, times A critical. A critical, this is the value of A at critical temperature and at critical pressure. Then alpha, we can calculate alpha using this formula. We have this M, this is a parameter in terms of the eccentric factor, and we have TR. This TR is any property that we have the R subscript, it's called reduced. So this is reduced temperature. If we have PR, so this is called reduced pressure. Okay. And by the way, omega can be found at appendix C, or if you don't have information for omega, there's an equation that we can use to calculate it. What is TR? What is PR? The reduced temperature. This is the temperature of your substance divided by the critical temperature. Reduce the pressure. This is the pressure of your substance divided by the critical pressure. So any property divided by the critical value of this property will give you the reduced value of the same property. Reduced is property divided by the critical. Okay? So these are the set of equations to calculate A and B, the parameters that we are needing to substitute in Soave equation and solve it. If you have Peng-Robinson equation of a state, we have different equations. Again, we have an equation to calculate B, terms of T critical and T and critical pressure. A is calculated from this one. What is AC? This is AC we have here, and this is the equation that we are using to calculate alpha. there is an equation to calculate K. This equation in terms of the eccentric factor. You can find it in Appendix C. If not, then we have an equation to calculate the eccentric factor. Still, here we have reduced temperature, and reduced temperature divided by critical temperature. Reduced the pressure is pressure divided by critical pressure. So far it's clear? Any questions? So if you have any problem, I'll ask you to solve this problem, use Soave equation, use Peng-Robinson equation. So what you need to do, just to substitute in all of these equations, find the value of parameters A and B, and then substitute in the equation to find like any property you have. Any questions? Okay. We will stop here today. On Monday, we will just give a quick overview on the 3 chapters we have, because we have chapter 1 to 7 will be in the exam. We will go over these 3 chapters one more time quickly. Then we will solve equations on the cubic equation of states. Okay? Thank you.